if you go talk to manufacturers, right, like ask them about tool and die making, and they will call it, like a dark art, basically. Sure. And we basically want to like suss out how much of that is really true. So if it does turn out to be only 90% automatable, right, in design, that's okay, because that's still an absolutely crazy precedent being set in terms of how much labor is being dumped onto a machine versus a person. And if like the remaining 10% is that highly creative, like explorative nature that only humans can bring to the table right now, that's okay. Die casting is notoriously bad with scrap rates. Like 30 to 50% is kind of like industry standard. It's like
30 to 50%. So 30 to 50% of the metal that you inject in is scrapped.
Yeah, it's a very interesting, problem at scale, because every time you want to, like a car, for instance, right? Like every new model of car has roughly like $1 billion of tooling that comes along with it.
$1 billion.
Yeah. So that includes like all the plastic components are injection molded. The sheet metal parts are stamped, right? And then the aluminum parts are die cast. So in those three categories, like the spend is roughly like even. So, 300 something million per category.
Welcome to Autopilot, a podcast where we discuss the past, present, and future of AI and automation.
From Atlanta, Fulton Passage.
That's one small step for man.
We explore how AI is creating and disrupting large industries in conversations with top founders, investors, and historians. I'm your host, Will Summerlin. Let's dive in.
Aaron, welcome to the Autopilot podcast. Thanks for joining.
Good to be here.
So before we get into tool and die making and all the chaos in deep tech, let's start with a little context. Can you share your background and what you're building at Atomic?
Yeah. I don't know how far back you really want to go.
Let's go back to high school.
All right. Yeah, I grew up in the Midwest from Cleveland, Ohio, and ultimately decided to not go to undergrad right away and worked a bunch of like weird menial jobs all over the place, and then decided in a more philosophical roundabout way that I wanted to study the meaning of the universe. So I went into physics, basically. I worked full-time while I was going through undergrad, so it took me a lot longer to make it out, and ultimately ended up finding some interesting like computer engineering and programming jobs like while I was in undergrad. And as I made my way out, I was actually, mass applying to PhD programs in a couple different areas, but my focus was in high energy physics, so in like fusion energy. And during that time, I had applied to one job, like a normal person job at Google, and I ended up getting it somehow. Like I went through the interviews, went out there, it was all crazy, and I decided to put grad school off the table and took that job. So I moved out to the Bay Area and started working out there. And I had a few different roles. Some of them were kind of like more IT, like back-end engineering and like ops related type work. And also worked on a team at google.org that doesn't exist anymore, but it was RE less than C, looking for ways to make renewable energy cheaper than carbon, basically. And that project was heliostats. They were trying to make scalable heliostat systems. So these are like a big reflective concentric circle rings of mirrors that reflect the sun to like a central collection tower. You've probably seen these driving on like 5 going out of the desert. And we were trying to make like a low-cost version of that. And I had only joined for a few weeks, but in that time period, this was when Eric Schmidt stepped down and Larry and Sergey took the company back over. And an interesting side effect of that was they shut down all the programs at Google that were not like computer science centric. So that program got axe murdered, and I ended up following the engineers there to Google X and working on the self-driving car project. And this was like, 13 years ago at this point. So those are like very early versions, not the Prius, but the next version after that was when we were, ripping apart Lexus SUVs and like trying to put the sensor packages on those as well. And so I worked pretty closely with a smaller team, at Google, most notably with like Anthony Lewandowski, and those guys had come from 516 Systems in Oakland over to start the self-driving car team. So they'd already been there for I think like a year or two at that point. But we had like a big garage that kind of butt up against like NASA Ames back there, and it was just like a big workshop. It was cool. But at that time, it was pretty apparent that was going to be a very long endeavor, right? And they were arguably like out in front at that time, like 10 plus years ago.
Yeah.
But we were like internally celebrating wins when like Nevada passed a law that we could, operate the car there and collect more like mileage data and stuff like that. So in my mind, it was really cool to be working on like the cutting edge of technology there. And this is obviously like a great problem to solve, but I knew it wasn't going to be something quick and easy, like at all. And the regulatory part was like a huge component of that besides the technology, obviously. So after working there for a few years, I decided to go back and actually like pursue a PhD in something, but like more applied in nature. I kind of had that urge to get my hands really dirty and build something. And I ended up zeroing in on a field called power systems engineering. And the whole background behind this is just like the electrical grid and the infrastructure and how to like optimize it. So it's kind of like an applied physics and engineering discipline. And we've obviously let, the electrical grid languish for quite a long time. It's going to be a problem where we need engineers there. And that's ultimately why I decided to, go into that field. I finished like a little bit more than half of my PhD before starting my first company, which was called Remesh. And this is a, AI before AI kind of company where we started it as a competitor to Twitter, actually. And the idea was that most social platforms were just like noise at like a large scale, right? You've got an insane amount of like comments and like replies and stuff onto threads and whatever, right? Like it just blows up at scale. And it's really hard to understand that. So we being myself and a friend from undergrad, he had built the foundational math and like algorithmic base of this idea, which was, can we take a group of people and put them into a conversation and represent all of their thoughts and opinions like in a fluid conversational manner? And so this turned into a piece of technology, right? And like me coming out of the Silicon Valley pipeline and coming back to Ohio to like do a PhD at Case, like we started talking about this, right? Like maybe we should, make a product out of it. He had already, done some like hackathons around it and tried to get it off the ground. And yeah, so we kind of like went in together and we're like, we're going to do this. And so we started building a company, and we learned pretty quickly that social is like a pretty challenging landscape in like, 2013, 14 time span. And we worked really hard at building up the platform to that point. I mean, like we got all the way to the White House, and they're like, oh, well, you're not like the scale of Google, so I don't know if we can really like use you. And it was fine. It was like really interesting to do that. But like our fantasy had always been, can we put the president into our platform, and like have the president speak to 100,000 Americans like simultaneously. Like that would be pretty sweet. Yeah. Because it's like a fluid conversation on the platform. And, ultimately, we ended up going through a couple accelerator programs. Like we did Techstars in New York. We did one locally in Cleveland too, which was an interesting experience. And then after we kind of got out of Techstars, we raised our first like seed round and like started growing the company. We pivoted into market research, right? So using this platform as a tool to do that kind of really direct feedback with a group of people is super powerful if you can do it instantaneously, and like all the insight that comes out of there is relatively deep. You get a giant data set within like 60 seconds. Yeah. So you can send in like a big consumer goods company and, maybe they're trying to do market research on a new product they want to launch. We could just bring in, the kind of demographic they were interested in, like survey them on the spot, but it's this conversational dialogue, right? So you don't have to come prepared with a survey, you just have a conversation.
Sure.
And you collect all this information, and it's really pretty interesting to see it unfold in real time. But that's what we built the company around, and grew it relatively quickly once we pivoted. And I spent about 5 years on the company up until we got, to like a pretty decent scale and did a Series A with a big tier 1 investor.
Yep.
And then I clocked out after that, basically. And yeah, getting up to even speed on like Atomic after I had left Remesh, basically I just wanted to reset for a little bit. Had a really small exit when I left and decided that, I'd do some like passion project. And my idea of a passion project was to do something that I had never touched previously. And this was making a consumer product. And I was actually pretty interested in making figurines for tabletop RPG games like Warhammer and Dungeons and Dragons.
Yeah.
And these are like hobbyist items, right? So they're very small, super high detail, high quality, like people spend a ton of money on them, like painting them, and it's an interesting hobby. But I thought I could make them, in pretty decent volumes, like pretty quickly, and rapidly turn out different designs and things like that. But I learned, unfortunately, the hard way that like conventional manufacturing doesn't work that way.
Sure.
It's not, it's not super easy to ship a new physical product, even a little toy like that, right? So, coming from tech and software, I learned the hard way. But at the same time, a light bulb kind of went off in my head, because this is, like 2018 or so. And I guess the thinking at that time was we have got to be at a point where, between machine learning, material science, robotics, automation, like all these things maturing and getting to a really interesting like last mover type of position, right? Like you can probably vastly improve manufacturing processes using technology. And I haven't seen a lot of startup companies trying to attack stuff like that. You've got really interesting examples of, a couple public companies trying to do some of this, but it's more in optimizing like the on-the-floor operations and things, right? Like set up a dashboard and orchestrate some stuff. Like that's only a part of the problem.
Sure.
So yeah, I really, dug into this and spent like a year calling and researching and going to like factories that would do this kind of stuff. Because initially what everybody told me, like my friends at big tech companies that still did hardware and everything, they're like, yeah, go to China, like go on Alibaba and find a supplier. And it's this magical black box and you like give them money and then your product shows up in a crate, a couple months later. It's not that easy, right? Like some people might argue with that, but I didn't have an easy time finding a good supplier. And there's so many like weird, challenging barriers to doing stuff like that, right? They have insane minimum order quantities. You can't just order 5,000, you have to order like 100. And if you can't sell that, then like you have all this dead inventory. And this is actually a really interesting problem because in manufacturing, there's tons of like dead inventory that just sits in ports and warehouses and stuff and never gets sold. But I thought this was fascinating. And the actual manufacturing process to make my, little figurines, I needed molds to actually make them. And so it's this kind of like arcane craft where, somebody sends you a CAD file of a design that they want to manufacture. And before even like going to manufacturing, they have to scrutinize your design for manufacturability, right? Like if you've ever heard of DFM,
I have not.
Yeah, design for manufacturability.
Okay,
so you need to actually design something so that it fits into a manufacturing process. And, assuming you do that well enough, you can now manufacture these things at scale, right? There are certain like angles and features on a physical product that you literally can't manufacture at scale.
Sure.
Or even in one-offs, right? But that's what 3D printing was supposed to bring us. So I really dug into the trade of tool and die making, which is, the tradespeople that take your design and translate it into the mold or the manufacturing tool that will ultimately make your product. And, in my mind, it's this kind of like huge bottleneck in the manufacturing process where if you could, take that process to commoditization, basically, the physical world would move so much faster. You could prototype things more quickly, you could manufacture things more efficiently, less waste, higher throughput, faster cycle times, all that kind of stuff. And it turns out that it's not just something in my mind, it's actually how the world manufactures a majority of goods, right? It's not just molds, but die casting for aluminum components and dies that do like sheet metal stamping and things like that. A lot of products are made using some kind of manufacturing tool that's like highly engineered.
So when we look at injection molds, is every mold unique to the product that's being manufactured in it?
Yeah, every single manufacturing tool that gets made is a unique snowflake, right? So if you look at it like an onion, in the very center of that is, a cavity that has to get filled with material like plastics or metal or whatever. The unique geometry is kind of what drives the rest of the design of the tool and like how complex it really ultimately gets. So it's a very interesting, problem at scale, because every time you want to, like a car, for instance, right? Like every new model of car has roughly like $1 billion of tooling that comes along with it.
$1 billion.
Yeah. So that includes like all the plastic components are injection molded. The sheet metal parts are stamped, right? And then the aluminum parts are die cast. So in those three categories, like the spend is roughly like even. So, 300 something million per category. To tool up a new car, it's roughly like $1 billion, basically.
Where's the $1 billion being spent? Is it on labor to actually design the molds? Is it on the raw materials to make them?
It's the whole supply chain of, doing that. So if you're a car manufacturer, you send all your drawings to the manufacturer. They go through that feasibility analysis where they kind of like pick apart your design, whether or not it's actually manufacturable, right? And a lot of times, even if you're like a high performance sports car, right? Like I won't name brands, but like, there are some many hundreds of thousands of dollars sports cars and $1 million, that deal with this problem regularly. They will have a very specific like spec on cars that they want to manufacture. And then the manufacturer will come back to them and say like, you have to tweak the design a little bit. And they're like, no.
The tool and die maker will come
Right.
back and say you have to tweak.
Yeah, because of basically like how complicated it really is at the fundamental level to achieve the geometry that they're trying to squeeze out of that manufacturing process, right? And you're not going to like switch to 3D printing that thing necessarily because it's not scalable. So if you're trying to make like maybe 20 to 100 cars, 3D printing might be a great exercise in doing that, right? At like super low volume. But if you want a reliable, consistent, repeatable process, you engineer a manufacturing tool to make that thing. So. Yeah.
What does the industry look like for tool and die makers? Is it consolidated into a few big players? Is it relatively fragmented?
No, this is very, I think we've heard this story a lot now, right? There's a fragmented supplier base, and there aren't really, monolithic players that do a lot of that. You might have larger contract manufacturers that vertically integrate like many different manufacturing processes, right? So like Flextronics, Foxconn, those types of companies will have some number of like processes that they have vertically integrated, and they probably outsource a lot of the other stuff as well to other suppliers. So there's the big, supplier pyramid of tier 1, 2, and 3, with the OEM kind of like sitting on top.
What are the labor dynamics like in the tool and die making industries? Is there a oversupply of labor? Are there labor shortages?
Yes, it's a very small pool, right, of like specialists that take decades to really, mature in their skill. And so when you go into the trade initially, you're kind of like a liability, right? Like you can only touch certain parts
Sure.
of the process until you show promise and you actually, get better at different parts. And you're exposed to the whole end-to-end process, right? Like of going from design to machining the thing and assembling it and putting it together to ultimately like producing parts out of that tool. But yeah, like the best tool makers in the world have a very thorough understanding of like the whole end-to-end process and how a tweak in a design ultimately changes the part that comes out, and how efficient the whole manufacturing process is. So,
how do they use technology today outside of Atomic? Do they use software? Is there any level of automation, or is it really just like whatever information they have inside of their brain over 10 years of experience is just being manifested in the mold?
Yeah, it's still very driven by the tribal knowledge, right? Like, if you think about it in terms of you're searching a solution space for an optimal design, right? Like, I want to manufacture the lid for this coffee cup, and so that's not a super complicated mold, but if you think about extrapolating that to like any of these other things that we see around us, right? Like, going from initially receiving that design to an extremely optimal tool design is a very lengthy process, right? So the better you are, the more skill you have, will shorten that, right? It narrows the solution space down, basically, because you understand all the parameters.
Sure.
And so the tools that people use now, we've got like CAD software, there's different CAD platforms and simulation tools. So usually you need generally like two humans, one that actually does the design in CAD, and they can use all the tools and plugins in their CAD package, versus like the simulation engineer who will take the design and simulate it and show the designer, like, here's where you have some problem areas, change the design. So they'll have to go back and iterate on that, and it takes a long time to go back and forth, right? And in usual production environments, you don't have the time to do those iterations because it takes so long, right? And a lot of that is based on the simulation effort and the design effort, and just knowing how to get to the best design as quickly as possible.
How long does it take normally for like a traditional tool and die maker to run through that process?
So it's a giant spectrum, right? Like, on the lower end of complexity, it could be, a week or two, versus a extremely complex part, which could take, months, like 3 to 4 months of back and forth. So that also assumes that you have the DFM component knocked out already.
Yeah.
So the DFM component can also take like weeks or months too, depending on if you have to tell your product designers to go back to the drawing board and tweak a design. So the whole thing ultimately is very painful and long.
It's not software where the iterative loop is a few hours.
No, not yet.
Not yet. And we'll get to Atomic and how you guys are fixing this in a second. But if we look at the incentives of the buyers of tool and die products, so an auto manufacturer, for example, assume I'm a large auto manufacturer and I'm buying tool and die products. What do I care about most? Do I care about the cost, the time it takes to actually get the mold back? Do I care about the efficiency of the mold? Like, what are the incentives that drive my buying behavior?
So each industry has different key value propositions that drive their motivations, right? So like in automotive, the longest lead time component will drive that, right? So if there's one critical component on a car that takes an extremely long time to design and engineer the tool for, and then make that part, right? Like, that holds up the entire rest of the manufacturing process. And that could be like a metal stamped part, right? Or like the car bumper. Car bumpers are notoriously challenging to make a good tool for, right? So you see anything that's able to shorten that whole window for automotive is something that's huge for them. And they also like to prototype things too, but it's expensive to prototype. And in consumer, right? Like, if you can arguably get a new line of products from a big CPG company into market faster than your biggest competitor, that's huge, right? Or like a new shoe from an apparel company, right? Like, if I can deliver a new shoe to market 2 months faster, right, than some of the biggest apparel companies in the world can, I don't know how to quantify that, but I know it's worth like millions of dollars to them to do something like that. Plus all the other compounded effects that you get, right, which is like supplier overhead to manage the relationships with the suppliers and like go do the back and forth, product delays, right? Like, there are plenty of examples where a manufacturing tool was not engineered well enough, right? Or like the parts coming out of it had defects, and maybe like an entire car line had to be paused basically in production until they re-engineered the tool to get it out the door. And that happens less frequently, but it still happens, right? And you've got a lot of like waste in the manufacturing process as well. So, you know, die casting, for instance, is notoriously wasteful when it comes to like the scrap rate. Like what's the percentage of parts that come out of a die cast, right?
Can you explain what a die cast is?
Yeah, it's the same thing as an injection mold, but it's for an aluminum part, right? So you make a mold, close it together, and shoot liquid aluminum inside of it, cool the part down, open it, pull it out.
Sure.
Like the gigacast, right? Like that's I think one that a lot of people probably know or have seen. Die casting is notoriously bad with scrap rates. You know, like 30 to 50% is kind of like industry standard. It's like
30 to 50%. So 30 to 50% of the metal that you inject in is scrapped.
Yeah, you can just remelt it and do it again, but it's still, that's how bad it is.
Is that because of errors in the cooling process? Like
yeah, it's really challenging to actually control the physics of what's going on inside there, right? Because you're shooting a bunch of super hot liquid, you know, metal into a cavity, and you're trying to be very precise with how it's cast. And you need to control the heat exchange, right? And ensure that there's no defects in the part, basically, on exiting. So it's pretty challenging to do that.
That's great. So if I'm making something in a die cast, 30 to 50% of the time it comes out, it's going to be
Bad.
erroneous, and I'm going to have to throw it away.
Yeah.
That's insane.
But you can recycle the material. So,
Sure.
yeah. But it adds overall, right? Like it compounds to how long it takes you to make more of those parts.
Yeah.
And this is much lower in injection molding for plastics. It's like 5%.
Okay.
You know, like under 5% is like industry gold standard. You know, you don't want worse than that. And then in stamping, it's also pretty low, but still very challenging to get right.
Yeah.
Yeah.
So let's get into Atomic a little bit. You kind of talk through the way that the process is typically managed at a traditional tool and die maker, right? A lot of human intuition, tribal knowledge, maybe some software. You guys are taking a different approach. So maybe you can talk through the process that Atomic takes and the advantages of doing it your way.
Yeah. So if you go back to the analogy of like the solution space and trying to search within that, right? What we're trying to do is build software that can search that solution space as quickly as possible, right? But in order to do something like that, you have to understand how manufacturing tools are designed and how they are manufactured and how they perform. It's the same set of tribal knowledge that a human learns over these like decades of time, right? So for us to be able to teach a machine how to do that, we have to replicate the process of teaching a human. So there's a gigantic component of basically like high ceiling skill trade knowledge transfer from humans that know what they're doing into software. But when you do something like that, it comes with bias, right? If you or any big car company came to me and dropped off like 1 billion mold designs, right, of like all of history, it's cool, like you definitely get some benefit out of that, but you're gonna see like the human bias in the designs. And if you actually scrutinize one design over and over again, right, like you can find efficiencies to actually squeeze out of it. So the nature of that problem becomes kind of like subjective, artisanal like skill versus like a deterministic physics-driven model, basically. Like if you have some kind of like set geometry that you want to manufacture, you have to understand how all the machined metal is going to be put together. I mean, like how it's even going to be machined in the first place and then assembled together and then work in a factory. So I know people love talking about digital twins, right? But this is like a whole nother level because you're really trying to reproduce what the designers understand how to do in software, basically. And so this is distinctly different from a plugin in your CAD software that can like automatically like draw a surface or extrude a feature or something, right? Like that doesn't take engineering skill. That's like it's an extrapolation of geometry, right? And so the true nature of the problem actually requires like this intuitive human engineering skill. So there's a really fine line between like, does that actually mean human intelligence, right? Or can we actually, objectify the problem with deterministic properties.
Sure.
Using physics to drive the design.
How much of the ability to do this is based on sort of the advances in AI and machine learning over the last decade?
I would say a good number of them. I mean, like, there's a lot of advanced techniques that are, like gradient-based search methods to find different types of optimizations in problems. So a lot of traditional optimization techniques are, like a forward and backward pass or some kind of like gradient-based search. Those types of methods don't really have like a memory, so to speak, right? So it's not like a true AI. Sure. And it's not necessarily like a foundational language model either. So these are, you can apply transformer-like techniques to these types of problems, but in different areas. It's all about like how you actually construct the problem. But yeah, I would say overall, a lot of what's happened even in the last 5 years is helping to advance, techniques in what we're trying to do.
So just to replay this, you're basically teaching a machine to design injection molds the same way the best humans would be designing injection molds, or
Better.
tool and die products across the board. Better.
Yes. The idea that like there's some holy grail optimal design for like every individual snowflake geometry that you feed it, right? We want to find that design as fast as possible, and the optimality of that design means that it flows through the rest of the process like very efficiently.
Would a fair analogy be like how AI was able to beat the best Go player in the world, not because it was sort of playing with the same strategy, but because it went way out into a solution space where humans historically hadn't played?
Yeah, I think I do think that that's kind of fair. I would probably get pushback from people because that's the area that we're searching, right? Is like we know that it is kind of like an art. If you go talk to manufacturers, right, like ask them about tool and die making, and they will call it like a dark art, basically. Sure. And we basically want to like suss out how much of that is really true. So if it does turn out to be only 90% automatable, right, in design, that's okay, because that's still an absolutely crazy precedent being set in terms of how much labor is being dumped onto a machine versus a person. And if like the remaining 10% is that highly creative, like explorative nature that only humans can bring to the table right now, that's okay. And it's possible that language models or some derivative of them could potentially be that last 10% one day, right? Like that's true human intelligence replication, which is very hard to condense into like anything other than being this generalizable nugget of intelligence, right?
Yeah. So if we sort of go all the way through the process to the end design and the end mold that you're producing, how is it better for a customer? Is it better because they get it faster? Is it better because it's cheaper? Better because it's a more efficient design?
All of that. Plus, right, like I think a story that you'll begin to hear as more companies start to appear that look like us, and right, like you'll see a large fragmented market, right? That's very challenging to deal with. In manufacturing, it's even worse, right? Because you need consistent, repeatable results. The better suppliers are always at capacity because people know that they're good and they produce good work.
There's a supply-demand imbalance.
Definitely. So if you can use technology to guarantee that, right, and make a scalable solution out of it, there's no limit to like the amount of demand you could really pull with that. So it simplifies a lot of the other stuff that I talked about before, right? Like all the overhead it takes to manage suppliers, getting to market faster, right? Like waste in the manufacturing process itself, delays, like all of that stuff kind of diminishes in the face of, a very improved vertical simplified solution that does that problem. So it's a very multi-dimensional thing, and it's hard to quantify for even, the largest manufacturers on the planet.
How have you guys done any market sizing? Like how big is the tool and die making market?
So if you look at the parts that are made using this methodology, it's like a little over $500 billion a year.
Wow.
and it's challenging.
And that's the end parts. That's the cars,
That's
coffee
plastic
cup
parts.
lids. Okay.
Yeah, if you're only talking about plastic parts, and this traverses the spectrum of, high-end production, high volume, all the way down to lower volume prototyping stuff. That whole spectrum is, like 600 billion, something like that. And the tools that make all those parts are scaled back by like an order of magnitude. So,
Sure.
And it also kind of depends on, how much of it is being bought. It's not like a one-to-one parity basis. So if you're like a high volume manufacturer, you might actually buy 2 or 3 extra tools for capacity, right? So like if your primary tool goes down, you just slot the other one in.
Got it.
So a lot of times it's not just like, I need one part, I buy one mold. I mean, it is, but for bigger companies, they have, risk mitigation and volume considerations they might need more than one. So they usually do buy like capacity tooling to cover that.
That makes sense. And you guys actually have a physical factory in Michigan. Why did you choose to vertically integrate the entire process and sell a customer mold versus building the software and selling it to tool and die makers?
Yeah, so it's a good question. It's a very common, line of reasoning. It's actually a more challenging engineering problem to build software that can generalize to this level of accuracy into any shop in the world with any set of equipment, with any, operators behind them or whatever. So the top of the stack is really just how can you generalize that problem? And for us, it comes by way of putting all the machines right in front of the software, basically, right? So it's going to learn specifically from each individual machine that we feed to it, right? Because there are different like processing parameters and things that you can tune at the machine level that help influence better design, basically like upstream from there. So it's similar to how humans learn, right? Like they have to be put into the environment and learn the whole thing. So we're doing basically the same exact process.
It's almost like self-driving. It's easier to teach a car how to drive in a specific city than to generalize it across all of Earth.
Yeah, and this is another argument that I hear kind of frequently too, right? Which is like, why hasn't somebody just generalized and made like a self-driving, model that can work in any car? It's literally the same thing, right? You have to learn how the car itself works and how to move it through the world. It's the same thing with a factory. So it's a very analogous problem.
Is there efficiency to be gained in just like modernizing the actual manufacturing process? So moving beyond the design of the injection molds and actually like taking the raw parts and turning it into a mold. Are you guys finding ways to make that more efficient, or is that a pretty efficient state across the industry?
Well, yeah, so at the real heart of it, right, there's only so much efficiency you can gain in any manufacturing process, where that butts into, right, like raw material processing times and costs. So you can't really beat physics in a lot of ways. So like right now, today, there's only so many ways that we have to machine metal like super accurately and quickly. Until somebody comes up with a better way to do that, and at like high volume as well. So that's what we kind of build towards and measure, is like figure out where all those efficiency gains can be had, and what is actually meant for a human to do, and on what's automatable basically. So like the lower hanging fruit of automation is something that you do last generally. So this is a pretty, I think at this point, there's a lot of PTSD and learned, scar tissue from trying to automate things too quickly and too much. Like Elon famously has a quote saying, he automated Fremont too quickly.
Yeah.
And that was a disaster. So they had to like rip it apart and start again, and then automate like at the end, basically. So what we're trying to do is figure out, using a very similar framework, right, is like, how is it done? Rip it down, right, and then add efficiency gains where we can. And that comes by way of different types of automation, orchestration, right? Like the stuff I was kind of making fun of earlier, right? Like operation efficiency, orchestration is actually really great if you can do it well. Because ultimately, what we're trying to do is send a design through a manufacturing process. So if you can simultaneously design everything to spec, right, and you know that the gap between your like predicted and simulated result and what happens in the real world, once that starts like overlapping, that's what I consider a digital twin. Not when there's like a gap there,
Sure.
where you still have to figure out like what's going on in the real world. Like in our case, that's another reason to vertically integrate, right? Because we want to understand what's actually going to happen and how do we orchestrate it better. Yeah, not to mention that like, you know, as a venture company, we have to demonstrate, you know, good unit economics.
Sure,
so
of
a lot of this will
This can't be a 20% gross margin services business, right?
Yeah, so a lot of that has to, you know, ultimately bleed through into the P&L
Yep.
in terms of gross margin expansion and other ways of saving labor. So yeah.
Makes sense. If we zoom out a little bit and just look at kind of moment in time, we're in early 2024, you're at the intersection of maybe the two hottest areas of venture, AI and deep tech. If you go back to 2018, obviously deep tech was not a hot thing. You started the company. AI, you can sort of understand like the catalyst that got us to where we are today in terms of the excitement, right? It was really the decline in compute costs coupled with like transformer architecture. It's gotten us these very large language models that are now useful and actually solve a lot of hard problems, especially with the knowledge work. Deep tech, what's the catalyst that got everybody excited? It seems like all of a sudden like El Segundo blew up and now everybody in venture is in deep tech and all the crypto funds have pivoted to deep tech. What was the catalyst that got everybody excited about it?
It's a good question. I think, if I'm going to be honest, it's kind of like when the bottom fell out of, you know, SaaS companies, basically.
Yeah.
When you look at like the market retreating from those types of companies, which, you know, I like to think of as are better as like a cash flow business than they really are as like a margin business, ultimately. I think that, you know, there's still a ton of money floating around looking for stuff. And with the, you know, like the macro environment of what's going on politically, there's a lot of charged, you know, energy around this urgency in having to make things, right? Like we talk a lot about our inability to make artillery and submarines and drones and things like this. And also just, you know, we've got more visibility into the physical world now and like how it's stagnated and seeing interesting things come online, like humanoid robots and self-driving cars and rockets going into space. Like that gets people hyped up. So I think you've got a big Venn diagram happening here of like different factors. You know, there's some macroeconomic exertion happening. There's definitely like a political kind of force happening there as well. And then we're seeing more and more innovation in the physical world too. So I think people just, there's cycles, right? Like it's very cyclical in nature. And I think people are kind of tired as well of, you know, going to work every day, working on like ad click optimization
Sure.
and that kind of stuff. Like I don't personally know how long I could do something like that. So there's, we know that there are more interesting problems in the world, and if we can build, you know, venture scalable companies around those things, like I think people are way more interested in challenging real world problems too.
And some of these markets are huge. I mean, global enterprise software spend is $1 trillion a year, which is big. But if you compare that to the broader economy, like there are many industries that are much bigger than software that have had little innovation in 30, 40, 100 years.
Yeah. I would say manufacturing is obviously, you know, I'm biased, but, you know, a very ripe industry for this because it's, you know, 4 to 5 times larger just from the United States and China alone, like in value add GDP being produced, right? It's like $6 trillion or something like that. But it's a very challenging area to actually marry technology together with manufacturing because it's a slow, painful process. But ultimately, the people that do that well enough and get those things to like break out into scale, those companies will, in my mind, no question be like this $1 trillion layer of manufacturing infrastructure that's super flexible, adaptive, and scalable. So I'm excited, obviously, about building in that layer.
It's a hard problem to solve in many cases, right? Like you're dealing with hardware, not just software, and comes with more complexity. You've learned a lot of lessons, I'm sure, since 2018, building the company up. You raised $17 million in one of the hardest fundraising environments the last decade as a very large seed round, which was impressive. And obviously now you have a physical factory. If you kind of take all the lessons learned through that, and you could go back to day one, 2018, give yourself one piece of advice, what would you have told yourself?
Yeah, it's challenging. I think one of the more, this is tough for me to say just because I would have approached fundraising a little bit differently, but I'm also not really a known quantity, right? Like in the world of technology, but it's harder for first-time founders to go out and raise money like AI companies are doing now. But I think that a lot of companies that are coming up in this space deserve similar attention. It's really hard to underwrite these kinds of companies because, quite honestly, I don't think many people have the sophistication of understanding how to even model the marriage of like technology and manufacturing on some level, right? Like the immediate inclination of just saying like, oh, CapEx bad, is like just a natural thing that happens, right? In my mind, after running a SaaS company, I'm like, oh, OpEx bad, right? Like my engineering, sales, and customer success team burned through more money than I even know, right? Like,
Yeah.
I can have a factory that allows me to never actually go to zero anymore now, which is kind of an interesting concept, but nonetheless, you still have to make the whole operation scalable in some way. So I would think like approaching the fundraising dynamic and conversation in a way that, like it's an evolving space even right now. Like I have these conversations on a weekly basis. So I would like to pass that back to my former self for sure, because, having it more of like an exploratory kind of fundraising environment, moving, through these steps like more pragmatically is good. But I think ultimately these companies have to be evaluated differently.
Yeah, I like to make fun of my friends in venture who just think you just apply a 10x multiple to ARR and that's how you should look at businesses. Like there's actually value in building a long-term financial model and understanding unit economics. And you're right, some of these businesses are more complex, but the opportunity set is larger. And a lot of them, I think, will end up being vertical sort of monopolies, right? Like winner take most outcomes. And so you can build huge companies, but the underlying metrics are probably going to look a little bit different than a traditional SaaS business. And I want to correct you on one thing. You said you're not a known entity in tech. Maybe you weren't. You are now. Now you're quite Twitter famous, and you're sort of the godfather of the new wave of deep tech companies. So maybe you weren't in 2018, but you certainly are now.
We gotta do something.
Yeah.
Spread the good word. Yeah. I mean, I'm really excited about where the space is moving, and I think there's still a ton of opportunity. So.
I agree.
Yeah.
So if people want to follow the journey or get in touch with you, where do they go?
Just hit me up on Twitter.
What's your Twitter?
A physicist, all one word.
A physicist.
Yeah.
Awesome. Well, Aaron, thanks for joining us.
Thank you.
All right. Go build manufacturing.
Thanks for tuning in to the Autopilot podcast. If you're using AI to create or disrupt a large industry, I would love to learn more about your story. Drop me a line on Twitter or go to our website, apv.vc. If you want to support the show, the best ways are to leave a review wherever you're listening and subscribe. The Autopilot podcast is part of Turpentine, the podcast network behind Moment of Zen, Turpentine VC, Age of Miracles, and more shows for experts by experts in tech.